Welcome to the last lecture on molecules in motion. We are continuing with the parameter of derivation of the various diffusion parameters for a perfect gas, and that too from the kinetic theory. This derivation was not initially taken, though this derivation was not listed in the part of your syllabus, but I thought we have taken similar kinds of derivations, so it could be included here. So, what we have the lecture in the last class which we talked about was the derivation of the thermal conductivity coefficient kappa, in which we are talking about the energy being transported through collision, and for that what we had taken that each molecule is carrying an average energy of say E equal to nu kT, where nu is the parameter depending on the type of molecule which we have, and K is the Boltzmann constant, T is the temperature. Nu is going to be 3/2 if you have monoatomic gas particles. So, nu is to be designated as to type of particles which we are having, molecules which we are having, either monoatomic, diatomic or complex, which we have taken up in details. What we have taken in assumption is the number density is uniform throughout the system. Only parameter which is changing in the process is the temperature. So, if the temperature is changing as the molecules are moving or from one region to the other, then what they are doing, they are actually transporting energy along with them. So, if each of the molecules are carrying or particles are carrying certain amount of energy, the total energy transported by them will be the average energy of the molecule carried by each molecule into the total number of molecules which we have. And on find out the number of particles which are transporting, we look into a diagram like this, where the area of interest is A. We are looking into this region only. We are saying that the particles are moving with the relative speed c bar, and in time delta t they travel a distance of c bar delta t. So, all the molecules in the volume element A into c bar delta t is going to be colliding into this surface, and the average number of impacts or collisions that can happen in this region can be given by 1/4 NC, and total number of molecules contained in this, it has to be multiplied by the volume element. That is, the volume element is that is the distance into area, and that is area A naught into c bar into delta t. So, this is going to be the total volume element. All molecules contained in this region will be actually colliding on the surface. To find out the flux of the particles which are moving from either left side or the right side. When they are moving from the left side, you see, if I project it on the distribution of energy versus distance plot, then this plot at lambda minus is going to be at higher energy, and the flow of energy is always going to be from higher to lower. So, if I what restrictions I have put, that the molecules are moving only one mean free path distance to come into collision at the area of interest. So, the mean free path we have designated to be as lambda. So, this is the distance the molecules are traveling to hit on the window. So, the molecules which are traveling from left side towards the window or from the right side towards the window have to have traveled a transverse length distance of only one mean free path, that is lambda. So, when they are so what we are going to be looking is to what is the net flux which is what is the flux of particles coming from the left hand side, what are the particles coming from the right hand side, and when they are going to be meeting at the area of interest, the net flux in the window is going to be the addition of the one moving from the left side to right side, plus the flux of particles with a particular energy moving from right side to left side. So, if I want to find out the average energy transported, I need to know what is going to be the transported energy. Transported energy at lambda minus z equal to z lambda minus is nothing but the energy associated with at any position is going to be nu kt. So, this is nu kt minus what? Nu kt into lambda, that lambda is the distance at which it is travelled, into the change in temperature with distance. So, what you have, the change in temperature into distance into the position gives you the location at which you are finding out what? The energy. So, it has to be multiplied by k nu, Boltzmann constant. So, similarly, we have for both the expressions the average energy transported at lambda equal to z equal to plus lambda. This is going to be a positive sign. So, net total opposing energy flux which we have and meet in the window of interest A0 will be nothing but the flux moving from of particles having certain amount of energy E moving from left to right to that of the flux of particles moving from right to left. If you remember, the right side is always a cooler side. So, cooler side molecules cannot move to the higher hotter region. So, the expressions which we write will be always having a negative sign. Flux is not a negative value, but what we are trying to say, the flux movement is actually towards the reverse from left side to right side. When we are talking from left side to right side represents a much hotter region. The particles moving from a hotter region and to cooler region is spontaneous. So, this will be positive and this will be giving a negative term. So, if you look at this, this is the positive, this is the term which I am associating with the location see at lambda plus, and this was at lambda minus. I am substituting those values. What I do get? I get these two cancelled off. I get twice of this value into whatever is constant outside. So, twice of this value means I am going to get a 2 cancelling off. 2 by 1 by 4 will be half. And why do I get a minus sign? I get a minus sign because I have a minus here generated, and this is also minus. So, if I have this total evaluation, the flux is going to be 1 by 2 nu k into lambda C into n. So, what we can compare now you compare these two equations with the phenomenological equation of the energy and temperature gradient. This is how it's related. Energy flux is proportional to negative gradient of temperature. This is how it's related, and what we have got from the net flux, we have got the net flux as 1 by 2 nu k lambda C n dt by dx. If I compare these two, before comparing I can rectify this. We can multiply by 2 by 3 for correction for taking into account long flight paths of the molecules, which we have discussed in the last class. We have seen that the distance which we are looking into for the molecules or ions to hit on the window of interest is may be considered low, but sometimes what happens, these molecules which are at close distance of collision with the surface actually has taken a long flight, and this in the process should have been buried or grounded as they have undergone previous collision. Okay. So, to take into that into account, to account for the long flight paths which should be lowering the flux of the particles. So, I have multiplied by 2 by 3. 2 by 3 into this whole thing gives you 1 by this parameter. If I compare this, then you can get the value of thermal conductivity. This is also minus sign, this is also minus sign. So, this is my value of kappa. So, the kappa is thermal conductivity it is nothing but nu k lambda into the relative mean speed into the number density. Okay. Now comparing the now you can, if you put the number density here in this expression, in this number density is nothing but the total number of molecules in the total volume of the container V, then total volume of the container V, we can rewrite that in terms of, what do you say, this is the V is the total number of, if I want to find out total number of moles, then I can multiply that total moles into the Avogadro number divided by n, this replacing in the number of molecules by the number of moles, then V by n is nothing but the concentration A. Okay. So, V by the n is the concentration. So, this V by n A, it is actually the reverse. So, we have A equal to V by A. So, A is the molar concentration, right. You have a look at this, how is it A coming to, A is equal to V by n. So, if it is V by n, then A is going to be in the numerator, okay, right. So, I can put that in terms of the Avogadro number into the A, the molar concentration. Again, you can, these are simplifications, you can further do it. Take your time and do it yourself. Repeating it doesn't matter, it doesn't make any sense, because I have derived these. Probably if you do it, you will also remember. Now, put the values of the molar specific molar specific heat, which is again defined as nu into R into Avogadro number, which is actually R, and nu into R, which I can change into R be replaced by Boltzmann constant into Avogadro number. So, R is replaced by Boltzmann constant into Avogadro number. So, this way thermal conductivity can be replaced in terms of CV. You just see, you can replace this value and this value with the CV, the molar specific heat at constant volume. So, you can put that. Now, you can do further simplification in terms of the collision diameter. Collision, if you see kappa, this is the expression where lambda is to be, we have done that previously, lambda is kT by root T, root 2 collision cross section area into the pressure into the Avogadro number. If you look at the simplification of A, instead of A, if you write down this, then you come to this expression where you can put in the kT value here and n value here, and if you divide by Na on numerator and denominator, you get this value. You do it until you do it, you will not be able to, because when I do it, I become clear, but it's very difficult to make you understand until you are doing parallelly with me. Okay, the last one is the viscosity coefficient of a perfect gas. So, for this calculation, what we have to look is the viscosity coefficient of the gas as the net x component of momentum brought to the plane. This is the plane of interest at say z equal to value lambda equal to 0, and this location. What is happening? The x component of momentum is brought to the plane from faster moving to the slower moving layers. Okay, this is the faster to the slower. So, if I am moving from faster to slower, on the average traveling a distance of say lambda, that is the mean free path in each direction. So, the x component of momentum is transferred to a plane from faster to a slower one on the average while traveling either lambda distance on the positive side or in the negative side. Okay, so this is what it is going to look like. As shown in the figure, molecules travel from right to left, moves from faster to slower. Okay, so as we move from right to left, we move from faster to slower, right? And when you are talking about a flow of liquid, when we say the layer which is at in contact with the container is actually supposed to be stationary. That's the slowest. So you can see, may take the container towards this side. So what we have a molecule traveling from right side to left side, right side to left side, moves from a faster layer to a slower layer, and in the process transports the moment and the x component of momentum to a new layer at x equal to 0, and the total momentum which is transferred is mx at lambda. Okay. Similarly, molecules moving from the left side, this is the left side to right side, since this is a slow moving to a fast moving, which is not possible. So we always get a negative sign to represent that the other way around is more spontaneous. That means from fast is to slower is what is more spontaneous. The transport to this new x at z equal to lambda equal to 0 is the position where it is going to be moving. That's the window of our interest, and the amount of momentum, x component of momentum transferred as we are going from this side to this side is going to be mv square at lambda x equal to minus lambda. So as faster moving comes from faster moving layer to the layer which is at x equal to z equal to 0, moving, so it comes from a faster moving layer to a slower moving layer. When we come from the right hand side, we come from the higher momentum region to a lower momentum region. When we transfer the momentum transferred can be taken as mx at lambda equal to z equal to lambda. So the distance which is traveled from right to left is the lambda distance. That's the minimum distance which can travel. That's the mean free path. Only those we are considering which is traveled only one mean free path. Similarly, we can have the molecules move from left to right. Here it is moving from the colder slow moving to the high moving, which is not really logical, but transports to a new layer. What is the amount of momentum which is transported? It is mx at lambda equal to minus lambda, z equal to minus lambda. Now, assuming the number density is uniform throughout all the layers, the collusion flask is given as 1/4 number density into the mean free path, and the molecules arriving from the left to the right, from the left to right, from left to arriving from right to left, from this side to this side, will on the average carry a momentum of how much? At this position, what is the momentum? That is the mvx at lambda z equal to lambda, and that is going to be something which is going to be the momentum at x equal to z equal to 0 into some distance where the velocity gradient is. The velocity gradient is in this direction, so velocity gradient x into z, because that is what momentum is getting transported. So what we will see to find out the average momentum carried by the molecules when they are moving from right hand side to left hand side, right hand side to left hand side, that means from higher faster moving layer to slower moving layer. What is happening? What is happening is that if you see the total number of total momentum which is undergoing change, it is at this point. At this point, what is the momentum change? That is the change, the momentum at this point, that is mx at mv at x z equal to 0, plus depending on location of the lambda, you can take depending on the concentration. If the concentration is uniform, what we say, the slope of change of the velocity, the change of velocity with distance along this into the distance which you have traveled, gives you the more or less location of your energy or momentum. So the momentum along this say right hand side to left hand side, this side will be the average energy which is the molecules are going to carry while moving from say m0 to m plus left right to left, and the value will be the momentum at x equal to z equal to 0, that is this value, plus the slope of change of velocity with z, the vx velocity with z, into the distance lambda into m. Before the molecules arrive from the therefore those molecules arriving from the left to right will be bringing in an average momentum of what? This was corresponding to say right hand side to left hand side. Here we are corresponding to the energy corresponding to from left hand side to right hand side. So from left hand side to right hand side, the molecules which is going to be arriving at the interest of windows z at z equal to 0 will be nothing but mass into velocity at x component of it at the condition of lambda minus lambda equal to the momentum at z equal to 0 minus the slope of the say velocity in with distance graph, the slope of that into the velocity, the mass of the gas into the what do you call mean free path. So if I can take the net flux, which is the x component moment in the z direction, can be taken as the flux at z direction is nothing but the flux of the particles having the momentum mx along this mx average energy of transferring momentum of mx at a distance say lambda. Lambda is the mean free path, one mean free path distance from the last collision. So what we have this, and now we want to find out the net flux of the x component momentum at the window of our interest, that is z equal to 0 at this location. Okay, what will be that? If you see, if you write down the what is the momentum transfer when the molecules are moving from the left hand side to the right hand side, and what is the movement of materials or particles from right hand side to left hand side. Right hand side always being say faster. So right hand side will always impart higher momentum to that of the component which is slower at lambda minus z minus lambda. So if you take this flux means this plus this, the flux at the say left hand side to right hand side, and here right hand side to left hand side. If I take two positions, and the position is of our interest, that is z equal to 0. At this position the z component of the momentum can be given as the net of this and this. What happens? You can see this is going to cancel off, this is going to cancel off, this is going to cancel off. Again you are left with twice of this and twice of this with a negative sign. So this is also negative, this is also negative. So you are left with twice of it. So twice of that will give you 1 by 2. You have to multiply by 2, so it becomes 1 by 2, and you get a negative sign because they are negative. Okay, so here what we have, the flux of x momentum is proportional to the negative of the velocity gradient. See what we are getting. We are again approaching a phenomenological equation where we are having the flux proportional to the negative velocity gradient. So if I compare the two expressions, if we compare the two expressions, we have this as the constant. This constant can be taken to be this one, right? So that is what I have written. Now again if we take into account the long flight paths into consideration, then the flux will be reduced. So for that we have to multiply by 2 by 3 the correction factor. The correction factor, if you multiply by this, then you get 1/3 mm into the root mean square velocity into the it is the relative mean velocity, and this is the what do you call that, mean free path. So you can further modify this in terms of various parameters, in terms of Na and the molecules, which is molar concentration of the molecules, and you can do that by substituting the lambda values as well. Lambda is the mean free path, and you get an expression like this. So these are also expressions which are modification and simplified, but this is the one which you get directly from the without further manipulation of the equations. You play around with the equations to get various expression in terms of molar mass, in terms of molar concentration. Also you can do it in terms of the molecular mass into the say diameter of the cross section diameter. So all of these you can see, you can utilize to find out the various values of the parameters which is associated with the phenomenological equation. What we have done today, so we have taken all the diffusion parameters like diffusion coefficient, we have done the thermal conductivity coefficient, we have taken the viscosity coefficient, and we have tried to put in very crudely, but we have tried to put in using the kinetic theory model. We have tried to put in the expression for each, so that we can justify how it is got. So these are previously taken. How they are changing is previously discussed. Please go through those, because there are very important parts. This is only a derivation. Probably if you understand, then you do not even need to think about it much. But how each of the parameters, how temperature, pressure is affecting each of the say diffusion parameters is very important. You have got the expression here, and is this from this expression, what do you extrapolate and can think please do such problems. Please try to solve problems using these particular diffusion parameters, because numericals will be on these type of questions, these type of expression, because various try to keep your units uniform, so that if you are having a unit problem, then the values of eta or kappa or whatever d you are going to get will be not proper if you are not maintaining the units properly for each of the parameters which you have in the expression. This more or less covers what we are supposed to be doing in this syllabus. Please do more problems, please solve some equations. Whatever I have done here in the class and previously, it is mostly taken from two books, Atkins and Physical Chemistry by Atkins, Peter Atkins, and Physical Chemistry by Castellan. You can go through them, but please try to solve more some few problems. Please go through the transparencies by each line, because each line conveys a lot of information. And all the best. Thank you so much.